Okay. Hi, everyone, and welcome to the Secure Boot and Remote Firmware Updates webinar. I'm Kajal Sakota, and I'll be your mediator for today. This webinar is presented by Daniela, who is a senior engineer at wolfSSL. All attendees will be in listen mode only. There will be a Q&A session at the end of the presentation. Please, however, feel free to enter any questions in the Q&A box to be addressed during the Q&A time at any point in the webinar. This webinar will also be recorded and made available via a YouTube link following the presentation. And now, without further ado, I present Daniela.
Thank you very much, everyone. Thanks a lot for joining this webinar today. I'm Daniele Lacamera. I'm an software engineer at wolfSSL. And today I'm going to talk about secure boot and remote firmware updates. So first of all, we know about numbers, right? And IoT. We have about 30 billion of IoT connected devices. This is data from early 2020. About 127 new IoT devices connected to the internet every second. So it's about time we start asking how did IoT security go all these years? Security is still the missing S in IoT, or are we able actually to identify security threats that are specific to IoT? And are we implementing the best standards and technologies? Something that's very important in other contexts and sometimes overlooked in embedded development is do we understand deeply what vulnerability management means? Vulnerability management, it's about using the best technology up to the latest standards, but not only, because once the product is released, even if it's using the best and most secure solutions out there, such as wolfSSL, it's still a software project, right? So it will have drawbacks and issues that might come up later on, and even the most robust and secure TLS implementation that has no known vulnerabilities today may become vulnerable in the near future. Due to the active research on new attack mechanisms and ways to circumvent security protections that we developers face. So what happens in this scenario is that all these connected devices that share connection with the internet or with the M2M infrastructure of some kind have new security requirements, and one of those security requirements is certainly the possibility to update your secure software and all the firmware that's running on your device at any time. So we see clearly that secure remote updates have become a security requirement for IoT connected devices. What are the risks of developing embedded systems nowadays? Especially when we are talking about updating firmware. So we are adding functionalities and we're probably adding also attack surface. So what we're trying to prevent is that an attacker, an authorized user would try to run unauthorized firmware on the target. That often happens because there is weak or no authentication for what concerns the authenticity of the current running firmware. The attacker may or may not have access to the debugging interface at that point and extract information about how the firmware is being validated if we are not using the best possible secure strategy as we. Then there are other, of course, points of access possible towards our device, like for instance, extracting data at rest from a storage and non-volatile memory, and this is due often to weak or no encryption in non-volatile memories or wiretapping bus due to no communication encryption, for instance, in communication between two microcontrollers on the same system. There's other possible attacks, of course, is code injection, arbitrary code execution, which is often because of safety failures in the software. So buffer overflows, intentional stack collisions that can be generated by an attacker when poor memory safety measures are in place, or where, for instance, systems where dynamic memory allocation is overused, or the stack is not properly segmented. And of course, there are other types of attack, fault injection attack, which include voltage glitches or electromagnetic interference. We know about all these kind of potential security threats. And however, we have different attack, which consists in intercepting our remote updates while they have been transferred, and or injecting faults, well-known faults to the host microcontrollers, even to the point, depending on the effort and the investment from the attacker, to decap and using a scanning electron microscope to reveal some hidden information that are stored in here. So this is just a few examples of what can go wrong if we don't follow the guidelines for securing a system properly. And securing a system, of course, starts from boot and firmware update. About firmware updates, the first questions that we asked ourselves, is there a standard way to implement firmware updates? And but there is an effort from IETF as a group, update for the Internet of Things, which is a working group within the IETF, which defines a standard, a draft for a standard, that's the SIT architecture, which concerns firmware update architecture for the Internet of Things. Now, the term Internet of Things within this context is used to identify especially microcontroller-based systems, and there are a few requirements and guidelines that are being standardized in this context, and especially let's say that the entire concept is based on a minimalistic bootloader, which has high reliability, and it's agnostic on the way the images are transferred, because it does not contain any communication libraries, but it's just there as a tool to facilitate the installation of these firmware updates that have to be validated for integrity and authenticity, and we will see how. So basically, within these guidelines, it's clear that the bootloader must provide a secure mechanism based on asymmetric cryptography. We do have a lot of experience on cryptography at wolfSSL. That's in fact our core business, to secure data at rest, but also and especially communication. And we do have a great knowledge about these kind of secure mechanisms. And so especially we saw a good match with what we are doing and the kind of problem that are posed by secure boot and secure firmware update transfers, etc. So what is the normal approach for products that want to integrate secure boot. It's normally what we saw a lot is do it yourself, secure bootloader. So a secure bootloader made from scratch. But the secure bootloader, unfortunately, it's a complex project, and it's often it's too easy to underestimate the effort that has to be spent on testing and checking the reliability and all the corner cases of a failed update, for instance, rather than malicious attacks, and testing every single kind of situation that may present on the field might be more time consuming. That's what estimated in advance. And of course, it's not about just about the embedded development, but we're also talking about key management, support for an existing chain of trust, trust anchors. We talk about that, secure elements integration, and of course, the integration with the development lifecycle of your developers, with end-of-line testing, production deployment, factory images rather than first update on the fields, etc. So there's often a lot of costs and challenges that are not taken into account sufficiently in these kind of projects, and that the time to market hides all these procedures that are have to be completed before the device can go to the field. Especially if your secure bootloader is the immutable part of your embedded system, and it's not something you can update and of designs. And there is, of course, support and maintenance on the field, running after defects and issues that might the impact of on what is going to be considered a commodity for most embedded projects on the main project itself. So the question you have to ask yourself is, would you write your own TLS library or your own TCP/IP stack or your own real-time OS? Well, probably the latest being the easiest among the three, from scratch for your embedded project? And probably the answer is no. So why would you decide to write a secure bootloader if only we had a generic solution that's good enough for the average case and for every case in the market? That's why we felt the need for a universal secure bootloader when we started writing wolfBoot about a year and a half ago. And we wanted the portability across all 32-bit microcontrollers at the beginning, even though you'll see that this support has grown in the meanwhile to larger systems. We wanted SHA-2 or SHA-3 just to verify the integrity of the system. Of course, you're transferring a firmware update over sometimes unreliable channels, or things may happen during the transfer. So you want to install updates that are that can verify against integrity, against a SHA digest. We wanted, of course, public key firmware authentication to verify the authenticity. So in order to say that the firmware is genuine and it's coming from a trusted source, there is a way to do this, and it's checking the signature of the firmware against the public key that's stored in the trust. We wanted the smallest footprint as possible in order to run on the smallest 32-bit devices. Think about Cortex M0s or similar interfaces. Of course, we cared a lot about memory safety to reduce the attack surface, so no dynamic memory allocation. All the buffers are sized at compile time. And we wanted interrupt disabled at all times in order to have a static, predictable execution flow, predictable times of execution, etc. And of course, the reliable firmware update mechanism. That's the main feature besides the authentication for the bootloader. So the The firmware update mechanism, so the transfer of the image, as we said, should be independent from the update transport mechanism. And a fallback mechanism is suggested by the draft, and it's something that we decided to implement in order to be able to roll back to an existing previous version in case the update is yes genuine, but it can't lead to a working system for several reasons. So on these premises, we created wolfBoot, which is the open source universal bootloader. And the scope at the beginning was solely for IoT devices. So following the strict requirements, at the moment we started the code, it was in draft version 4, now we're in draft version 8. It runs on most 32-bit microcontrollers. Our first port was for them, of course, for the most popular platform for embedded development on microcontrollers. We did later on a port to RISC-V RV32, and just recently we introduced a compatibility with 64-bit systems, which means that we are able to interact with the boot chain of more complex devices, for instance, running Linux or anyway having a virtual memory manager and even support device tree loading for Linux kernel and execution levels, ARMv8 execution levels, in order to guarantee sandboxing of the different components. For instance, if we want to interact with an hypervisor in trust zone and be able to boot an operating system on a higher execution level. wolfBoot is OS agnostic because it integrates easily with any existing bare metal or real-time operating system solutions. And as just stated, it provides support for kernel booting, Linux kernel booting, and rootfs updates in embedded Linux. It provides easy chain of trust integration because it works both as a standalone bootloader, which is using a single trust anchor, which can just simply be a public key that's stored in a non-modifiable area of the flash. We will see later, and staging the final application straight from stage 1. But on the other hand, there's also a possibility to integrate with existing secure boot chain. For instance, if your hardware vendor is already providing a first stage bootloader that has some feature, for instance, I don't know, ERC checking or checking against the symmetric key for the next staging, you can create wolfBoot in such a scenario just to add and provide publicly authenticated updates as an added feature to the existing boot chain. And then the firmware authentication happens at boot time. So at every boot, the bootloader will check that the image that's stored on the boot partition has not been modified, and it's still valid, authentic, and let's say a valid signature. There is support, optional support for secure elements, and this comes directly from wolfcrypt, which is our crypto library, which supports many crypto hardware accelerator and secure elements different kind from different multiple vendors. It's too long to list over here. And we do have support for TTM 2.0 devices via wolfTTM, so all the operations that are normally performed in software can be offloaded from the bootloader straight to the wolfTPM library, which will enable the communication with an external TPM device, which will can function both as a hardware accelerator and as a trust anchor to store the public key in a specific storage location. And of course, small and safe parser, as we already mentioned, no dynamic allocation that's allowed in the code. We care about code safety because we know about different types of attacks to secure boot that are performed at this level that often are related to exploiting very well-known code safety violations that are common, unfortunately, in many embedded projects. wolfBoot is capable of updating itself. The draft from IETF is clear about this point. It's something they advise not to do because it's not normally it can't be done in a reliable way while the bootloader is executing. Updating itself may make the system unstable, make the system not able to boot anymore if there is a power failure. While on normal firmware updates, power failure are not a problem at all because the bootloader is capable of resuming any operation it was doing, even the most critical sector swapping exactly from the point left, as we will see later. So the bootloader update is a kind of emergency procedure, and it's also useful sometimes to revoke trust anchor that's related to a private key that has been compromised on a server, kind of emergency procedures. But it's normally something that we provide, yes, as a feature, but it's not recommended, especially if the system is not reachable, physically reachable. For the rest, we do provide easy key management and provisioning. The keys are key tools that are distributed together with wolfBoot, allowed to create keys and sign firmware updates, both from C or from portable C that can be compiled for any system, and Python 3 tools. We expose the same functionalities, and we even have a mechanism to integrate third-party key provisioning, which is already foreseen in these key management tools. So you can basically extract just the manifest header that has to be signed and can be signed using an external signing step that can be a third-party tool or a hardware device that's capable of signing digest for the firmware header, which means that wolfBoot is very flexible regarding provisioning. Even if you're using the easiest case, which is you are the owner of your own keys, and you're the sole owner of your own keys, and you decide what's to be signed and transmitted as a valid update or not. And also those cases where there is third party, it might be a vendor, it might be a service provider, a cloud provider, that acts as a trusted authority for participating in signing your firmware as an extra step for validation. wolfBoot, as all of our projects, is actively supported and maintained. Team wolfSSL is working full-time on new features, bug fixes, new platform support, improvements, new features that come from feedback on the field, or new technologies. We have a long backlog of features that we are integrating already. Of course, as with many other products, probably you already know, wolfSSL offers support packages. We have different tiers of support, up to 24/7 support, so we can give you support on the field and give your customer support on the field for what concerns issues related to boot in this particular case. wolfBoot is portable thanks to the hardware abstraction layer that reduces to the minimum all the target specific code. The target specific code is mostly, if not exclusively, used to access internal and external flash drivers, which might or may not be based on an existing board support package that can be usually as easy as a few lines of code altering the value of a few CPU registers. And as most of our projects, probably all of them, all the source code and all the examples, secure firmware update, different cases of secure firmware updates are available with copyleft on GitHub. And of course, as the sole owner of the copyright of this software, wolfSSL is able to provide proprietary licenses to integrate the secure boot mechanism with any project with any license, including a commercial proprietary project that you might be working on. So let's have a look at the system architecture. On the left-hand side, you can see wolfBoot in light blue, all the components of wolfBoot itself. You see that the only external components would be a flash driver. wolfBoot already includes tons of different flash drivers for the most common microcontrollers and the CPU platforms from many different vendors. I invite you to check our GitHub page for an updated list of the supported targets. But as I said, the only target dependent code resides there, so it's pretty easy for us to come up with a as long as in the supported architecture. So some of the components you can see on both sides. wolfcrypt, as we mentioned, is the crypto library that provides all the crypto algorithms that are used for validation, authentication of the firmware, and integrity, etc. The public key trust anchor that may be, for instance, in the simplest case, filed in the wolfBoot code as a buffer containing the public key. The requirements from the security point of view are about this part. Optional secure elements and hardware acceleration driver, public key accelerator, and this little libwolfBoot, that's a shared code. That's code that's shared also with the application, which normally contains just a few, let's say, commodity functions to access the current version number of the firmware that's running. And optionally can also be used by the application to access the wolfBoot hardware abstraction layer, which means that it makes it easier for the application to store the update, the firmware update that's been received from a remote location. On the right-hand side here, the firmware architecture, we assume this is a secure system. So the application is solely accessing, it's only accessing the internet secure sockets, so through this TLS API that's exposed by wolfSSL. wolfSSL will make use of probably a TCP stack. We'll see this is not even a requirement, especially on smaller systems. And then a TCP IP stack will use a specific network driver to communicate to the other endpoint. So this is a bit the architecture that we expect from a secure system that's running TLS for all communication and has an integration with a bootloader through this small library that's shared between the two. How the key management work? In the easiest case, I said you are the owner of your own private key, so the private key stays on your server. It's never shared. It's never shipped with the device itself. The public key is stored on the target. Sometimes called the anchor store, and it's accessible by the bootloader, of course, because the bootloader has to perform signature verification. In some cases, this is not needed. If you're offloading the signature verification step to an external device that might also trust anchor store itself, then the bootloader doesn't have to access the public key in that case. As we said, there is no revocation mechanism provided by default, and the only exception is bootloader updates. And yeah, in the most common case, in the most basic case, let's say, the entire security depends on the private key being kept secret, and that's used to sign the updates in your backend or in your infrastructure that has the task to produce and send the firmware updates for your firmware consumers, in this case, devices. There's a second tool besides the key generation, which is the sign tool. The sign tool attaches a manifest header image. The manifest header contains metadata about the firmware itself, and including the firmware version. The firmware version is part of the verified payload. So basically, the signature will also cover this part, so that it's impossible to counterfeit the firmware by tagging it with a different version number. So it's not possible for an attacker to pretend that a firmware that might have been intercepted earlier as a different version that's stated that the one that's stated on the original manifest header that's being generated by the sign tool. As we said, wolfBoot relies on something called trust anchor to embed the public key that's used to verify the signature. But what's exactly a trust anchor? A trust anchor is one kind of object that's described in a RFC6024 and represents the authoritative entity, which is normally consists of a certificate or a public key. And the public key is used to verify the authenticity. So the signatures for different components in the system. So you can have different elements in the trust anchor. So you can have more than one public key, and each of those is used for might be used for different purposes. And when you do this on an embedded device, the public key are not remotely accessible when the device turns on, and you rather have a trust anchor store. So it's trust anchors that are stored locally. And of course, this means that these trust anchors, the public key that's used by the bootloader must be mutable. So there are additional requirements from suit about the trust anchor store, because trust anchor store in our device that's implementing security must resist modification against unauthorized insertion, deletion, and modification, which means basically that nobody must be able to alter your public key. Otherwise, the entire verification project is compromised by the alteration of the original public key. What is used for this? The flash readout protection that's often provided by your hardware manufacturer is sufficiently secure for most use cases. Sufficiently secure because it does not prevent all types of hardware attacks. And we know already of many devices that are on the market where this flash readout protection has been compromised. So basically, you can't just trust the fact that there is a write protection mostly more than the readout protection that's provided by your hardware manufacturer. And that's the very reason why secure elements may also implement trust anchor store, which have a slightly better degree of preventing the alteration of the trust anchor itself. So the trust anchor store can be implemented in secure elements, and these secure elements might even have been provisioned with an existing, let's say, an ad hoc public key that's been created during manufacturing process. So many manufacturers provide this as a service. So your secure elements come with a public key that's been created for you during the manufacturing process, and each device might have the same key, so that you're able to use the same trust anchor on all the devices to validate your secure updates that might involve a TPA, a Trusted Provision Authority, to also sign or co-sign the firmware update together with you. In the simplest case, as we said, the key is generated once, the key pair, the private key is kept on the server. The public key is put in the trust anchor. It might be on the device. So wolfBoot sources and the public key are combined. A linking step, you can have a wolfBoot, and if the flash is not writable, you can have a sufficiently secure trust anchor for that. From that point on the server or on your infrastructure, on your developer machine, you can compile a new firmware and combine it with the sign tool together with its version number and the private key that you previously generated to have an authenticated firmware. That's the only firmware that's allowed to run on a device because it passes the check against its public. What concerns the update management, there are historically two possible approaches, and they are both supported by wolfBoot, regarding how to partition the available space in your non-volatile memory in order to host both the current image that you're using as you're booting on your device and the update that might be available from it. So the AB approach, in the AB approach, you have two equivalent partitions, often on the same physical device, and they share the same hierarchy level. And the update is installed. If you're running on the partition A, you're receiving the update on partition B, and vice versa. When you're running on partition B, the update will be stored in partition A. This is a bit tricky when you're running on microcontrollers. So the alternative is that the active firmware always boots from the same location, which is called the boot partition. And the updates are always stored on a second partition. And the content of the two partitions is actively swapped during the installation after the update has been validated. And in case of fallback, of course, second swap operation. This might sound a bit more complicated, but it has a lot of advantages for microcontrollers scenarios where physical memory mapping constraints exists, which means that if you want to use the AB approach in a physical memory mapping scenario, you will have to provide two different firmwares, depending if your device is currently running on A or B, in order for the firmware to know at compile time from which address it will be starting. So it introduced this kind of execution in place constraint that had to be known at compile time, more specifically by the linker. And moreover, it doesn't allow the external non-volatile memory, such as SPI external flash, because those devices normally don't have the possibility to execute in place. The exceptions, of course, on the market, but it means that you're not going to be able to run the application from anywhere in your memory mapping, which is actually the preferred mechanism, so the AB mechanism on CPU systems, or for instance, embedded Linux systems or other VNM powered systems, where basically you can use an arbitrary memory mapping and use virtual memory so that you can even compile position independent Linux kernel, whatever OS you want, and that would be possible to be loaded from anywhere in your virtual memory mapping. So coming back to the boot update partition mechanism, in the simplest case scenario, we have both partitions on internal flash, plus these other two partitions, one at the beginning of the flash, and that contains wolfBoot itself, and that's the beginning of the flash executing space. And the boot partition and the update partition will have the same size, so that we can swap the content of the two when we receive an update. The good thing about this strategy is that, as we said, update and swap partitions can be mapped on an external non-volatile memory. Swap partition is a very small partition, as big as the biggest sector between among all the non-volatile memory ports that you're using. So normally in the order of between 512 bytes to up to 4, probably 8K, and this is used to swap the content of the two partitions in place while the update is being processed. So these pictures kind of summarize the stages before and after the update, when the two images are swapped in place, thanks to this little swap partition in the end. And this is, of course, covering the case where both partition, the update partition and the boot partition, are on the same physical memory. But of course, as we said, this can be different. And if something goes wrong and the success of the booting the firmware version 2 here is never confirmed, upon next reboot, wolfBoot will swap it again and restore the original status before the update. The application entry point has to be moved in your embedded project, so that's the only modification required to integrate the bootloader in your lifecycle. Basically, you have to reflect the fact that there is a partition now at the beginning of the flash where wolfBoot is running, and the firmware should be compiled to start at the very well-known location in memory. This is how the manifest header looks like. It contains a signature, it contains a SHA-digest, in this case SHA-256. Of course, the signature size depends on the algorithm choice. Yeah, it contains a number of information that are useful. For instance, the version itself, or the timestamp of the compile time, and a number of other fields that are not in this picture. I'll just skip this for a matter of time. I'll just go over it very quickly. At the beginning, this is the example of a real-life use case IoT product release cycle with wolfBoot providing remote firmware updates. So at the beginning, you flash wolfBoot using the JTAG, then you can flash the same way a factory firmware that's been signed using the tool still in your factory scenario. At this point, you can basically get rid of JTAG interface, because you're not required to write anything on this flash ever again from from a local from a local debugging interface, and we rather use the a remote connectivity to transfer new update firmware. So normal operating condition wolfBoot will verify the integrity of the current firmware, one that's being flashed in factory, and every time it boots up, it will just check that the signature is valid. And then when a remote firmware update is available, it will be a task for the application to download it to the update partition. At that point, wolfBoot will verify the update, swap the two images in place, keep the previous firmware in case something goes wrong. It can swap back again and restore the original situation before the update. This is the default logic flow. It's a very small flow state diagram. There is a panic situation that verifies by default if there is no valid firmware in either of the two partitions. Of course, this can be easily changed because it's the application logic of wolfBoot, which is just a few lines of code that uses all the components that are available. So you can write your own logic flow, which might be different, for instance, for A-B partition. This is the default for boot update strategy. It's one of the default logic flows that is the one that we use for microcontrollers, basically. As we said, the swap operation can be interruptible on most platforms, except a few exceptions where there's no possibility to add zeros to the flash without erasing the entire sector, because we do use some flag mechanism that increases the numbers of zeros in a specific byte on the partition to mark the status of the swap or the update mechanism in general. We talked about the secure boot, which is of course, the core part. I will spend a few minutes about this, talking about the secure firmware updates. What are the issues we solved so far by wolfBoot alone? So providing a secure and reliable update mechanism, key management tools, so key generation, signing, integration with provisioning, detecting and discarding invalid or corrupted firmware updates, detecting and discarding forged or non-authentic updates, managing interaction optionally with hardware accelerator, TPM, secure vaults, and all the devices that are supported by wolfBoot. What we actually haven't faced yet is preventing firmware updates to be intercepted, because this requires encryption, and ensuring that only authorized device can retrieve the updates, so that no non-authenticated device can't access the service that distributes the firmware update. So, what are the secure protocols for IoT nowadays? The most of them are based on TLS, of course, which is and hopefully on TLS 1.3, which is recommended the latest version by IETF. Unfortunately, not a lot of TLS implementations provide that. We can say that we were the first commercially available TLS stack to provide TLS 1.3 support, just when it became a standard back in 2018. wolfSSL is a library that provides TLS 1.3 security components to secure the connectivity of IoT devices, and it's mostly OS agnostic and adaptable to any transport happening. But we also offer, on top of wolfSSL, a whole ecosystem of tools for securing MTM and IoT. I will just mention the most important ones. This is the entire ecosystem that we have. So wolfSSL is for sure the central part. We have the wolfcrypt crypto library, but you can see the flexibility here of integrating with any TCP/IP stack or any custom transport layer to this interface that's based on a very easy to implement callback mechanism that can be integrated with any real-time operating system or bare metal implementation or existing POSIX like socket interface. And on top of that, of course, we can run on a number of different data link layer. All of those that I could think of, I put them here. But of course, if you have custom data links, as many of our customers do, like custom radio or custom wired protocols, we are able to work with really small packets using fragmentation. There's always a solution, even for the smallest system, probably using DTLS instead of TLS, or EDP, etc. But the important thing here is about all these application layer components. So we offer state-of-the-art connectivity towards any backend or a commercial grade cloud infrastructure. So these kind of components are what realize the link between your application implementing any of these modules or any custom protocol on top of TLS that you can imagine. So secure protocols for IoT, I mentioned the most popular solution that I use nowadays to synchronize and update firmware, and they are more or less the same as the one used by IoT devices to exchange data with cloud or like HTTPS, SSH, and MQTT, of course, over TLS. Why are those popular? Because they are standard protocols, being standardized. Some of them are used in completely different scenarios that have been adopted by IoT. Some of them, like MQTT, is specifically designed for IoT. They are easy to integrate with commercial existing cloud services, and they provide the best encryption and cloud authentication solutions. So quickly, SSH is the UNIX way of doing things. System administrators are big fans of it. We support secure copy. We can even support file transfer abstraction on that actually don't have a file system like RTOS, because you can implement your own callback that stores the file that's received from a SSH client into the device update partition. And you have to worry a little less about the other endpoint because it's compatible with all popular SSH clients. And of course, there's curl. Curl is probably in the top 10 the most used open source project of all times. It's very popular, especially in embedded Linux. There's hundreds of companies that are using it in embedded Linux products. Daniel Stenberg, which is the maintainer and main author of curl, is in Team wolfSSL, and he's the main author of TinyCurl, which is a HTTPS 1.0 only library, which is oriented for microcontroller. So it brings all the power of libcurl, of course, just for HTTPS 1.0, 32-bit microcontrollers. And that's nice because we can access REST APIs on the remote cloud servers or on our infrastructure. And the last one is MQTT. MQTT is lightweight standard secure message-based protocol. We do provide Wolf MQTT, which is our MQTT client library implementation, which is designed specifically for embedded systems. It's a very, very small footprint and it defaults on MQTT over TLS and port 883. So it's also easily integrated with many systems. And we do have code snippets that work with the major commercial cloud service providers. And we do support the latest standard requirements from MQTT, MQTT 5.0, and all the extensions for sensor nodes. This concludes my presentation. Just to summarize, we've seen that secure boot and develop firmware updates are common requirements in IoT. What we do, we provide wolfBoot, which is the key feature for implementing secure boot. It's a secure bootloader that uses public key authentication and provides a reliable update installation mechanism. Of course, we do have wolfSSL, which is our key project that brings TLS connectivity. And on top of that, we can build application using the other components, our other libraries, wolfSSH, TinyCurl, Wolf, and MQTT, which offer the best available solution for the state-of-the-art communication with cloud service. Thank you very much.
Alrighty, hi everyone. This presentation ran a little bit longer than expected. So I think we're gonna answer a few questions right now, and then the rest we will get back to you and answer the questions directly. One question we have is, what are the encrypting data in an NVM? If you have a mix of data that should/needs to be encrypted to protect the system or the data itself, and data doesn't need to be encrypted, is it better to encrypt the entire NVM or just the portion that requires encryption?
This is very interesting. It's the usual encrypt before sign or sign before encrypt. Let's say that there is no answer to this, no brief answer to this. My take on this is always to sign before encrypt and encrypt the entire NVM. Because in this case, it's like you sign a document, you put it in a safe. The signature part is not visible to someone who doesn't have the key of the safe itself. That's just to summarize, to answer as quick as possible to this one. But this is very interesting. It's an open topic, by the way. Depends on the case by case, I guess.
Yeah. Another question is, what are the standards for secure firmware updates?
Okay, yeah, we are aware of Trust Computing Group. It's not really a question. It's we know about that. But thank you for pointing that out.
Does one need TPM 2.0 when running on ARM with TrustZone?
No, these are two different fields, let's say. TrustZone is to separate, to sandbox every single component, every single staging part of the system, while TPM is used as a trust anchor in this case, and to offload security operations. So the two are not related. I've used TPM with system without TrustZone and vice versa.
How is your bootloader distributed as a source code? Or is it distributed as a source code?
Yes, it is distributed as source code. Yeah, all the code is available on GitHub, github.com/wolfSSL/wolfBoot and /wolfBoot-example, so you can see all the active development going on. Yes.
Okay. Current wolfcrypt can have large stack requirements with no dynamic allocation. Is there a large stack requirement?
We do have measurements on the stack. We're talking about a few kilobytes, 2 or 3 kilobytes, and this is always well known at compile time. We have compiler warnings when compiled with GCC if the stack exceeds the expectations. So you are always able to size your stack in advance at compile time, so you will know how much stack the bootloader is using. And of course, depends on the algorithm that you choose to include in the build, because we support multiple.
And then I think we're going to answer 2 more questions after this, and the rest
Okay,
will.
a quick one, if you don't mind. You mentioned that interrupts must be disabled during bootloader. How do you do network I/O without interrupt? Again, we don't do network on the bootloader. This is something that's stated in the specification of the draft, that the bootloader doesn't have to be a connected application. The bootloader must be working on an update that's been received by the application. This is for multiple reasons. First one is that you don't want an entire TCP/IP stack to live inside your minimal bootloader implementation because of safety reasons. And another one is that there are so many different data link protocols out there that we can't just code the bootloader around one of them. So we want to cover everything from Ethernet to Bluetooth Low Energy, going through LP1, OSS 7, whatever kind of connectivity you want. So this is we don't see a bootloader as a component that's actively connected. It's just interacting with the flash device.
Okay, that's all the questions we're going to answer for today. We will email you with the answers to the other questions. Thank you so much for joining this webinar. If you have any questions or anything else that might come up, please email us at support@wolfSSL.com, and please also follow us on Twitter and Instagram at wolfSSL. And as a reminder, after this webinar, I will be emailing everyone a link to a recording of the webinar, so you can go back and check over things if you'd like. Thank you so much.